We're going to be looking at exponential functions. If you haven't yet, I'd encourage you to pause and get stuck into these three puzzles. Try them out in a few different ways. See if you can code something if you can't see an easy way through, but have a play with them, spend some time, and when you have, come back. I'm not going to give away all the details of these puzzles here, but suffice it to say there is a particular number that is relevant to all three that we'll be finding more about as we go through. Continuing from the last video, we're trying to identify a few more elementary mathematical functions which we can find the derivative of. We've looked at some trig functions, we're now going to look at some exponential functions. And 2 to the x seems like a good one to begin with because it's relatively easy to sketch. I've marked this one in along with various points, 1, 2, 2, 4, 3, 8, and so on. Now, one way to estimate the derivative at different points would just be to draw on some chords, the chord between the point 0, 1 and the point 1, 2, for instance. And that's quite nice because we can immediately see the gradient of these chords. The gradients don't quite match the y coordinates, but if you look closely, you'll find that the gradient between x is 0 and x is 1 is approximately 1, or at the very least somewhere between 0 and 1. The gradient of the curve matches the gradient of this chord, which is 1. And then the gradient of the chord between x equals 1 and x equals 2 is 2. Between x equals 2 and x equals 3, the gradient is 4. So, like I said, the gradient of the curve doesn't quite match those, but there is something exponential about those gradients. Now, so far, we can't say for sure, but it looks like the derivative of an exponential function will itself be exponential. That suggests that this function is not just growing at an increasing rate, but that the rate at which it's growing is growing at an increasing rate, and the rate at which that rate is growing at an increasing rate, and so on. In fact, a good thing to try at this point will be to jot down a geometric series like 1, 2, 4, 8, 16, and then look at what you have to add every time to get from one term to the next. Now, with a quadratic sequence or even a cubic sequence, if you look at the sequence of differences, what you add to get from one term to the next, and then you look at the sequence of second differences, what you add to get from one of the differences to the next, if you go far enough back through the layers, you'll eventually bottom out and you won't go any further. You'll get to constant terms and then you'll get to zeros after that. That's because the rate at which a quadratic changes is linear, and the rate at which something linear changes is constant. The rate at which a cubic changes is quadratic, and the rate at which a quadratic changes is linear, and the rate at which a linear changes is constant. The rate at which a constant changes is 0. But if you try that with a geometric series, you'll find yourself just going in circles, really. The gap between 1 and 2 is 1, the gap between 2 and 4 is 2, the gap between 4 and 8 is 4. You're just generating another geometric series. So there's something fundamentally different about exponentials compared to polynomials. It seems like no matter how many times you differentiate, you're never going to get down to something simpler. Before we get properly into exactly what exponential functions do, let's look at this logarithm curve. So this one I've drawn represents the log base 2 graph. And again, I've shown some tangent lines on this one rather than trying to draw chords between the points. But again, it gives you some sense of what the gradient is doing. And we're not going to try to look in too much detail at what the exact numbers are, because this is just an example of a log curve. And I'm trying to get a sense of what any and all log graphs might do if I differentiate them. It's worth noticing, though, what's happening with the gradient when x is very small. X can never be negative, but as x gets closer and closer to 0, the graph goes further and further towards negative infinity, and the gradient gets closer and closer to positive infinity. It's a very, very steep positive curve at the beginning over here, and it becomes less and less positive and yet still positive. It never shrinks to a gradient of 0, but it gets as close to that as you like as time goes by. So we're talking about a function which somehow starts very, very high positive, but sort of asymptotic, and approaches but never quite reaches a gradient of 0. So our gradient function starts high and approaches 0. Now that sounds a lot like various graphs that we could draw. I mean, for example, the reciprocal graphs 1 over x, 1 over x squared, things like this tend to have that kind of behavior, where we've got an asymptote at x equals 0, the vertical asymptote, and an asymptote at y equals 0. So perhaps that has something to do with logs. Now, this is a useful graphic to pay attention to, because this is what happens when you ask GeoGebra to graph the gradient curve along with the real curve. If I ask for y equals 6 to the x, it'll draw y equals 6 to the x. That's the black line. But the blue line is the gradient function that corresponds to that. And you'll notice that when the base is low, the gradient function is below the original curve. When the base is high, the gradient function is above the curve. But if the gradient function and the original curve are to be in exactly the same place, we need that base to be exactly right. Turns out there is a number, we can get pretty close to it, even on GeoGebra, 2.718281828 something. It might look like it becomes a recurring decimal, but in fact it's an irrational number. And it's also the number you might have come across if you'd done some of the puzzles at the beginning. That's the number, as you may have guessed, which we give the name E to. That is Euler's number, or Euler's constant, the exponential number. And it's the natural exponent because it represents the perfect base for an exponential curve whose rate of growth is the same as itself. Every other exponential graph has, as we predicted, as its gradient function another exponential curve. But the really cool thing about e to the power of x is that the gradient of y equals e to the power of x is e to the power of x. If you look at any point on this curve, you'll find that the height of the curve corresponds to the gradient of the curve. So let's investigate e to the x using the more rigorous first principles approach and see what we can deduce about what its derivative ought to be. As before, when we looked at this with sine x, we're just going to concentrate first on the gradient of the chord between a particular point on the curve, x, f of x, and another point slightly further along, x plus h, f of x plus h. And then later we'll worry about what happens as we shrink h to be smaller and smaller. So we have f of x equals e to the x, and f of x plus h will be e to the power of x plus h. When we put that into the formula, we end up with this. Remember, the formula is nothing special, it's just the y step over the x step. It's the definition of gradient of a straight line segment. But now what we're going to try to do is isolate e to the x. E to the x is the bit that is not going to change as h changes, so I'd like to pull that out and see if I can separate out the pieces that involve e to the x and the rest. Well, I'm going to make use of the index laws because e to the x plus h is the same as e to the x multiplied by e to the h. And that means I can pull out e to the x as a common factor of that entire thing. And we're left with e to the h minus 1 all over h. So the question is, if we make h shrink towards 0, what happens to e to the h minus 1 all over h? Now, just like with trig, this is a standard limiting result that you would be provided with if you were ever asked to perform this proof in an A-level maths exam. But there is a very useful approximation that you can use that you probably won't have seen before. E to the x is roughly the same as 1 plus x. You could see this if you look at the graph. E to the x crosses through the point 0, 1, and at that point it has a gradient of 1. Before that point it's got a shallower gradient, and just after that point it's got a steeper gradient, but at that moment it's got a gradient of 1. And this, again, just like with trig, this is part of a longer infinite polynomial. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. So given that e to the x can be defined in this way, we can see that if x is very small, the higher powers of x become incredibly small. For instance, if x is 0.01, a hundredth, then x squared will be a 10,000th, and x cubed will be a millionth, and the values get smaller and smaller as you go along. As x shrinks, or as h shrinks, we end up closer and closer to 1 plus h. Well, if you have 1 plus h, and you take away 1 and you divide by h, we get h over h, which is 1. So the blue stuff becomes 1, and if the blue stuff is 1, then the gradient of that chord is getting closer and closer to e to the x multiplied by 1. Therefore, the gradient of the function f of x equals e to the x is e to the x. E to the x is its own gradient function. So if y equals e to the x, the derivative dy by dx is also equal to e to the x. This is a really important property. It's practically the definition of e to the x. It is the fundamental exponential function. Even the expansion of it, we can construct this expansion by trying to create a polynomial that differentiates to itself. If you start with that, you find yourself having to add more and more terms, and if you were allowed to have a polynomial that went on forever, then what you'd end up with is this one, 1 plus x squared over 2 factorial, etc., etc. Now, there's something really clever about this. This was not the only function we were trying to find a derivative for. We're going to see if we can leverage the fact that ln x is the inverse of e to the x to find the derivative of ln x. So if we do e to the power of both sides here, we get e to the power of y is e to the y, e to the power of ln x is x, because the definition of the natural log is the inverse function of e to the x. And now, because we know how to differentiate e to the power of something, just stays the same, we know that if I differentiate the right hand side with respect to y, I'll get e to the y. And on the left hand side, I can differentiate with respect to y as well, and I'll get dx by dy. Feels a bit backwards. We're used to having y defined in terms of x and differentiating everything with respect to x, but there's no problem with having x defined in terms of y and differentiating everything with respect to y. It works just fine. Now, it turns out dy by dx is just the reciprocal of dx by dy. Kind of makes sense. The rate at which x changes with respect to y is just 1 over the rate at which y changes with respect to x. But because I'm interested in the derivative of ln x, I want it in terms of x. So I'm going to make use of the fact that e to the y, which is what I've got on the right hand side here, that's the same as the e to the y on the line above, which of course is equal to x. So dx by dy is the same as x. Now I can flip it over, and hey presto, I've got dy by dx, 1 over x. It is a reciprocal graph, just like we felt like it should be. If y equals ln x, then dy by dx will equal 1 over x. It's a really weird result if you think about it. How we go from a log to a power of x when we thought we had the powers of x's all locked up seems a bit strange. The graph certainly seems to match. This is the log graph and the 1 over x graph plotted on the same axes, and you can see that as the log graph works backwards towards the y-axis, the 1 over x graph shoots up, also approaching an asymptote of the y-axis. But the difference is, as log approaches negative infinity, 1 over x approaches positive infinity. And that's because log has a steeper and steeper positive gradient. And yet, as we move to the right, the ln x graph has a less and less steep, but still always positive gradient. Just like 1 over x never quite reaches 0, ln x never quite reaches a 0 gradient. This is the next really important result to write down. If y equals ln x, then dy by dx equals 1 over x. And it's worth stopping for a second here and thinking about what would happen if you tried to integrate 1 over x using the ordinary rules that you've learned. We talked about how we can differentiate any power of x, and we can almost integrate any power of x, but 1 over x is a gap. 1 over x is not something you ever get when you differentiate, unless, as we've just discovered, unless you differentiate ln x. And that's because if you try writing it as x to the minus 1, and you apply the standard method for integration, increase the power by 1, then divide by the new power, you get x to the 0 over 0. In other words, if you try differentiating a power of x, you'll never end up with x to the minus 1. It just won't happen. So this was a gap in the powers of x when it came to integration. But now we've got this result. Not only do we know how to differentiate ln x, but we also know how to integrate 1 over x. And that's going to come in really handy later. Let's try a quick example. If y equals e to the x plus ln x, we're going to use the fact that if we can differentiate one function and another function, we can differentiate the sum of the two functions. E to the x differentiates to e to the x. ln x differentiates to 1 over x. And if we're going to differentiate it again, it would probably be helpful to write it as x to the power of minus 1. So we can employ our power of x rules. So we get negative x to the negative 2, but e to the x remains e to the x. In fact, you can do this as many times as you like, and eventually you might even start spotting a pattern. So the e to the x term will of course always remain e to the x, but the power of x is going to continually decrease as we go along, x to the minus 1, x to the minus 2, x to the minus 3, and the number in front of x goes from positive 1 to negative 1 to positive 2, and so on. Now this beast of a formula, you don't need to memorize it by any means. I've thrown it in as a bit of a bonus, but it uses some neat ideas that I think it'd be worth you thinking about. Where the n-1 factorial bit comes from, and what on earth the value of having negative 1 to the power of n-1 would be. You can test that this works when n equals 1 or 2 or 3, and if you want to get a proper sense of what's happening, try getting the fourth or the fifth derivative and see how it matches up with this formula. You'll start to see the factorial coming out once you've done a couple more of these. And this, the negative 1 to the power of something, this is an elegant way to construct alternating signs. Because if n-1 is even, then you're doing negative 1 to the power of something even, you just get 1, which just gives you the positive of whatever you had. But if n-1 is odd, then negative 1 to the power of that number will be negative 1. That's how we get a plus, followed by a minus, followed by a plus, the next one will be minus, and so on. Effectively, what's happening is each time a number comes down in front, it's a negative number, so it changes the sign. Now, the nth derivatives of ln x, these are the bits over here on the right, in case you're curious. We can look at what they look like on a graph. We go ln x as the original function, we have x to the minus 1 for the first derivative, 1 over x. The second derivative is minus x to the minus 2, or minus 1 over x squared. And the third derivative, positive 2 over x cubed. If you look on the graph, you can see we've got the 1 over x graph. I've shown the full graph, but of course the negative bits are a little bit weird. When we get to integration, we'll worry about what happens with negative values of x, because of course you can't have ln of a negative value. For the next derivative, it flips so that it's exclusively negative, negative 1 over x squared, and that's because the gradient of y equals 1 over x is always negative. sometimes very steep negative, like when x is a very small negative number, or when x is a very small positive number, and it's sometimes a very shallow negative, like if x is a very high number, large positive, or a very low number, large negative. When we go to the next one, we alternate back to being in the first and third quadrants. So it's similar in a sense to 1 over x. But that's representing the gradient of the minus 1 over x squared graph, and so on and so forth. So, to sum up, we know how to differentiate any power of x. If we can write it as x to the power of a number, we can differentiate it. We bring the power down in front, we reduce the power by 1. We can now differentiate sine x. That gives us cos x, just shifted to the left by 90 degrees, or pi by 2. So the derivative of sine is cos, and similarly the derivative of cos is negative sine. Whatever works for you to remember which way around those go, that's fine. I would recommend, if you have a method that is based on some kind of mathematical logic, it's going to help you in the long run. I've known people who try to learn it by saying it's the opposite way around to the way I think it is, which is a recipe for disaster, because as soon as you get used to it being the right way around, you'll start second guessing yourself. I would recommend a very quick sketch of the sine graph and then look at the gradient. Say, oh look, it goes 1, 0, minus 1, 0, 1. That's a cos graph, and then you're there. It doesn't take very long when you've done it a couple of times. We now know that e to the x differentiates to itself, and we got a 2 for 1. We managed to prove from that result that ln x differentiates to 1 over x. So what's next? Well, these are pretty much all the elementary functions. You can build anything out of these, more or less, and most of the things you're ever going to come across that you can describe mathematically, you will describe using some combination of these. But that's the rub. It's often a combination of these. So we have other ways to combine functions that we cannot yet deal with using differentiation. We can deal with numerical multiples of a function. In other words, if you put a number in front, we don't have a problem with that. We can have minus a third of ln x, because we can differentiate ln x to 1 over x, and we just leave the minus a third in there. So minus a third of 1 over x, or minus 1 over 3x if you prefer. 2e to the x differentiates to 2e to the x, and 3x squared differentiates to 3 lots of 2x, or just 6x. We can also deal quite comfortably with functions that are added or subtracted. So if I gave you this, it looks messy, but you just take it a piece at a time. You differentiate the x squared, you differentiate the sine x, and you'll take away 2 lots of whatever that was, and then you differentiate e to the x, and you'll add 3 lots of whatever that was. You can take it piece by piece, and it works fine. In fact, these combined are what we call linear combinations. So if we say you can have any linear combination of these functions, it means you can have as many of the first functions you like, as many of the second functions you like, and you can add or subtract them. So for instance, a linear combination of x and y would be something like 7x minus 14.5y. Some x's, some y's added together. Think of it a bit like a straight line. If I allow you a linear combination of x and y, and I say that that can be equal to a number, well, you've got yourself an ax plus by equals c, equation of a straight line. And we'll get onto more in linear combinations when you do matrices, if you do further maths. But there are lots of other ways you can combine functions. And one of the next things you're going to learn in differentiation is how to deal with a chain of functions, a function of a function, something which is applied to something else. So some examples will be e to the power of x squared, or sine of 2x is a slightly simpler one, or 2x add 3 in a bracket to the power of a half. If you add 2x add 3 squared, you already know that you can deal with it, but you have to do it by expanding out the brackets. Now if you got 2x add 3 to the power of a half, I suppose you could do binomial expansion, but you're going to get an infinite series, so unless you're prepared to just give an approximate answer, it's not going to be very satisfying. If we can find a way of dealing with the fact that we have a function we can deal with, 2x add 3, nested inside another function we can deal with, x to the half, something to the half, then we'll be able to tackle a whole lot more functions. Another thing is products of functions. If you multiply two functions together, x times ln x, or sin x times cos x, or x squared times e to the x, those do not behave in quite the way that you think they should. When you're adding or subtracting functions, to get the derivative, you just add or subtract the derivatives. But if you're multiplying, you don't just multiply the derivatives. There's something a bit more subtle going on, and we'll need to make sense of that through some useful diagrams. But there will be a way to deal with products of functions. It's not hugely complicated, but there is a subtlety to it that you need to be aware of. And in a similar vein, quotients of functions. This one is in some sense just a combination of the previous two, because you can think of sin x over x as being the same as sin x multiplied by 1 over x. And of course, e to the x over 2x add 1 could be thought of as e to the x multiplied by 1 over 2x add 1. But it's a bit of a mess sometimes, so we formulate a new rule that allows us to deal specifically with a function divided by another function. And then it's not necessary to know how to differentiate 1 over something messy, as long as you can differentiate the something messy. In fact, 1 over something messy can be dealt with using the chain rule anyway, but quotient rule allows you to simplify the process of a product rule combined with a chain rule. Now, tan x seems like it doesn't belong. How is that a quotient of functions? Well, if you look over on the left, you'll see that we know how to differentiate sin x and we know how to differentiate cos x. So although tan x may not look immediately like a quotient, under the hood it is. So when we learn how to deal with quotients of functions, that will be the key to differentiating all the other trig functions. Tan can be thought of as sine over cos, which will yield to the quotient rule, and cot, similarly, cos over sine, will be a quotient rule situation. Sec and cot are the same. We can think of it as 1 over sine x or 1 over cos x, and we can use quotient rule or we can use chain rule, because we know how to deal with 1 over something and we know how to deal with sine or cos. Once we can do those, we can pretty much differentiate anything that you can come up with. If you can write it out as a combination of adding, subtracting, multiplying, dividing, functions inside functions, in other words, anything you can write out with plus, minus, times, divide, brackets, we can pretty much deal with. Which is going to be quite a lot of stuff. Once you can do that, you can differentiate pretty much anything.